Hello students, welcome to my YouTube channel Dear Mathematics and also welcome to the chapter of complex number. In this particular session, we are going to discuss about a very important form of the complex number or very important topic of the complex number, and that is the representation of a complex number. Okay, let us start it. Representation of a complex number. Any complex number can be represented by three different ways. Any complex number can be represented by three different ways. The first one is geometrical form. The second one is vectorial form, and the third one is polar form. And we have to discuss one by one of all the three forms. So let us discuss from the first one, and that is the geometrical form. So geometrical representation of a complex number. Any complex number can be represented as a point in the xy plane. Any complex number z is equal to x plus iy can be represented by a point pxy on the xy plane, and that plane is called as Argand plane, or you can say that this is complex plane, or also you can write down it as a Gaussian plane. Okay, then let us discuss all of the geometrical representation of a complex number by taking the help of a diagram here. Okay, this is the xy plane, here it is the x dash, y dash, and this is the origin. Suppose this is the point pxy, and that is used for the complex number z is equal to x plus iy. So every complex number can be represented via a point on the xy plane, and let us join it. Okay, this is the point P. Then let us draw a perpendicular to the x-axis, and here it is M. So in this diagram, the given complex number z is equal to x plus iy is represented as a point pxy. In this diagram, the given complex number z is equal to x plus iy is represented by a point pxy. The real part of the complex number z, that is x, it is represented along the x-axis, and the imaginary part of y is represented along the y-axis. That means this is the distance y. and here it is x. So you can write down real part of z, that is equal to x, is represented along the x-axis. Then imaginary part of z, that is equal to y, is represented along the y-axis. The y-axis. The real part of the complex number will be represented along x-axis. Whether it will be on positive direction of x-axis or negative direction of x-axis, and again in the same case also imaginary part, whether this will be along the positive direction of x-axis or negative direction of x-axis, I will discuss it later. Then let us go through that topic. Whether in which quadrant the point will be plotted. Now let us go through the representation of a complex number in different quadrants. So let us go through the notes first. If x is equal to 0 and y is equal to 0, then the point Pxy will lie in the first quadrant. The second point is here, if x less than 0 and y greater than 0, then the point Pxy will lie on the second quadrant. Number 3. If x less than 0 and y less than 0, then the point Pxy will lie on the third quadrant. Fourth quadrant. If x greater than 0 and y less than 0, then the point Pxy will lie on the fourth quadrant. Then let us go through the fifth point, very important point. If the complex number is a purely real complex number, if the given complex number is a purely real complex number, then it will lie on the x-axis. That is, let z is equal to a plus ib. If b is equal to 0, that means the imaginary part is equal to 0, then z is equal to a, the purely real complex number. It is the purely real complex number. Will lie on the x-axis. On the x-axis. So x-axis is called the real axis. So x-axis is called as the real axis. Again, like this, number 5, we have to go through the number 6 in case of the purely imaginary complex number. It is the number 6. If the given complex number is a purely imaginary complex number, then it will lie on the y-axis. On the y-axis. That is, let z is equal to a plus ib. If a is equal to 0, then z is equal to ib. It is a purely imaginary complex number. Will lie on the y-axis. So, y-axis is called the imaginary axis. Imaginary axis. So these are all the fundamental notes of the representation of a complex number in different quadrants. Then we have to go through an example, and we can take some of the complex numbers and we can plot in the form of points in different quadrants. Suppose it is 3 plus 4i, and this is minus 3 plus 4i, and the third one is minus 3 minus 4i, and the fourth one is plus 3 minus 4i. Let us draw a diagram here of xy plane. This is the x-axis, this is the y-axis, and they meet each other at the origin. The first one is solution is here. Let z1 is equal to 3 plus 4i. The point P34 will be plotted or will be represented on the first quadrant. It is in the form of z is equal to x plus iy. Here x is equal to 3 greater than 0 and y is equal to 4 greater than 0. So the required point P34 will lie on the first quadrant. And here it is 1, 2, 3. 1, 2, 3, 4. And here it is the point P34. Then the second one, let Z2 is equal to minus 3 plus 4i. It is also in the form of z is equal to x plus iy. Here x is equal to minus 3 less than 0 and y is equal to 4 greater than 0. So the required point P minus 3, 4 will lie on the second quadrant. It is minus 1, minus 2, it is minus 3. It is the, okay, let us consider this point as Q because we have already taken P here. So this is the point Q minus 3, 4. Then let us move to the third point. The third one is here. Let Z3 is equal to minus 3 minus 4y. It is in the form of z is equal to Z3 is equal to x plus iy. You can also write down here Z2. Okay, you can also write down in the form of Z2. Here x3 is equal to minus 3 less than 0 and y3 is y, okay, here x is equal to minus 3 less than 0, y is equal to minus 4 less than 0. So the required point, suppose consider this point as r, minus 3 minus 4 will lie on the third quadrant. Here it is minus 1, minus 2, minus 3, minus 4. It is the point R, minus 3, minus 4. Then let us go through the fourth bit, and we have to represent plus 3 minus 4i. It is the fourth bit. Let Z4 is equal to 3 minus 4i. It is in the form of Z4 is equal to x plus iy. Here x is equal to 3 greater than 0 and y is equal to minus 4 less than 0. So the required point, consider this point as S. So the required point S3 minus 4 will lie on the fourth quadrant. Just let us plot this point here. It is plus 3 minus 4. It is 3 minus 4 and it will lie on the fourth quadrant. So these are the diagrammatic representation of the complex numbers in form of points in different quadrants. Okay, then let us consider another example here. Suppose I have taken here Z1 is equal to 3, then Z1 is equal to minus 3, okay, Z2, then the third bit is Z3 is equal to 4i, and the last bit is suppose here Z4 is equal to minus 4i. Solution. Let Z1 is equal to 3, that means 3 plus 0i, and it is purely real complex number, which is a, okay, you can write down purely real complex number. According to the properties of a purely real complex number, these complex numbers will lie on the x-axis, but we have to verify that whether the given complex number carries positive sign value or negative sign value. You can say that this is the positive 3. That means it will lie towards the right side of the x-axis, or you can say that positive direction of x-axis. So this is the point 1, 2, 3. The required point, it is the question number 2. Point is P30, and here it is P30. As it is purely real complex number, so it will lie on the x-axis, but you have to verify that whether this purely real complex number carries positive sign or negative sign. If it is positive, then it will lie along the or in the direction of positive direction of x-axis. Then let us go through the second bit. Z2 is equal to minus 3. The second case is happening here, and you can see that this is also purely real complex number. Purely real complex number, but you can say that this is negative 3. That means it will lie in the negative direction of x-axis. The required point is let us consider this as Q minus 30. This is minus 30. Then the third bit is here. Z3 is equal to 4i. You can also write down it as 0 plus 4i, and this is purely imaginary. purely imaginary complex number, the required point is, consider this as R and this is 0, 4, but we focus on the sign of this value, whether it is positive or negative. This is positive, that means it will lie in the positive direction of y axis. That means it is 1, 2, 3, 4 and this is R0, 4. Again, consider the last bit is here. Z4 is equal to minus 4i, that means 0 plus minus 4i. It is also purely imaginary complex number, but we focus on the sign of this purely imaginary complex number and it is negative. So it will lie towards the negative side or negative direction of y-axis. That means the required point is S0 minus 4 and here it is 1, 2, 3, 4, then that is 0 minus 4. And it is all about all of the problems in the form of a purely real complex number or purely imaginary complex number. Then let us go through some of the more fundamental data of this geometrical representation. Then let us discuss about a brief discussion or brief analysis on the modulus of a complex number by using this diagram. Okay, we will study modulus of a complex number and also its properties later after this video session. But in this video session, just let us make a brief discussion about modulus of complex numbers by using the help of this diagram. Okay, this is the point Pxy is represented for the complex number z is equal to xy. X plus iy. Then just let us join these points OP, PM, and you know that this is the distance of the OM is equal to x here, and PM is equal to y here, because the real part of the complex number is represented along the x-axis and the imaginary part of the complex number is represented along the y-axis. So here the length of the line segment OP, that means in this right angle triangle OPM, the hypotenuse OP is called as the modulus of the complex number and it is denoted by modulus of Z. And just we have to find out or we have to evaluate the value of modulus of Z here in the triangle OPM. In the triangle OPM, OP square is equal to OM square plus PM square. Then OP is equal to square root of sum of OM square and PM square. And the value of OP is equal to, here we have already discussed, it is the length of the line segment OP is called as the modulus of Z. It is denoted by modulus of Z. And the modulus of Z is denoted by like this. It is denoted by modulus of Z, and in the place of OM we can put X, and in the place of PM we can put Y square. Here it is. And also this is the formula for the modulus of Z. Okay, you may have a question, if there is a square root sign, then is there any positive or negative? Okay, there will not be any negative sign, it will carry only positive sign because length is never negative. As modulus of Z is used for the word or for the length of the line segment OP, and you know that the length of the line, any line segment cannot be negative. So the modulus of Z is here positive value of square root of sum of x square plus y square. Okay, you can also represent this in another form. Another form can be written in the like this manner. It is the real part of Z and its square plus imaginary part of Z, its square and its whole square root. This is another way of or another form to represent a complex number, represent the modulus of a complex number. Then let us discuss about the angle that is formed after the formation of the line OP with respect to the x-axis. Let alpha be any acute angle in the triangle OPM. Let alpha be any acute angle in the triangle OPM. Here you can write down tan alpha is equal to it is P upon B. That means perpendicular upon base, that means PM upon OM. So whenever we are going to put the value of PM and OM here, just we have to put a modulus symbol, because if any happens, because alpha is an acute angle, so tan alpha in between, acute angle means it lies in between 0 to pi by 2, and in this interval the trigonometric function tan carries only positive sign. If there happens any negative sign or occurrence of negative sign or possibility of a negative sign in the division of y upon x, then it will convert to be, or it will be converted to positive sign. So for this reason we have taken modulus sign here. So alpha is equal to tan inverse modulus of y divided by x. You can also write down alpha, the acute angle here, as a tan inverse imaginary part of z divided by real part of z and its modulus. You can also write down, and this is the basic form or formula for the evaluation of or the finding out of the acute angle alpha in between the line segment OP with the x-axis. So let us consider an example here. Example, let z is equal to 1 plus I, and then we have to convert it into the form of a point. That means we have to plot the corresponding point of this complex number, and then we have to find out the acute angle alpha of the line between the line segment OP and x-axis. So here it is the xy plane. Sorry, this is y and y dash, they meet each other at the point origin. Here 1 greater than 0, and also you can write down it is 1 plus 1 into I. Okay, both. Okay, let us write down in the descriptive form. It is in the form of z is equal to x plus iy. Here x is equal to 1 greater than 0 and y is equal to 1 also greater than 0. That is the point P11 will lie on the first quadrant, and here it is the point P11. This is 1 and also this is 1, and this is the perpendicular. Then we have to find out the angle in between the OP, the hypotenuse, and the x-axis. Let alpha be the acute angle. Let alpha be the acute angle made by OP with respect to the positive direction of x-axis. Here alpha is equal to tan inverse modulus of y upon x, and it is tan inverse 1 upon 1, then it is tan inverse 1. In place of 1 we can also write down tan pi by 4, tan inverse tan pi by 4, and that is equal to pi by 4. So the required angle is, pi by 4, and it is made by the line segment OP with respect to the positive direction of x-axis, and here it is alpha is a acute angle. So it is all about the geometrical representation of a complex number. In the next topic or in the next video, we are going to discuss about the argument of a complex number and also the very important principal argument of the complex number, and what are the differences in between argument as well as in the principal argument. Till then, thank you.